Welcome back. Hopefully everyone fared well during the storm. I did not assign anything last week, so if you did not see anything, don't worry, that's perfectly fine. We'll go ahead and pick up where we left off this week. If you have any issues, of course, please email me. But today we're going to talk about adequacy criteria, which is really just a way to at least start evaluating whether our test cases actually test what we need them to. All right, some learning objectives. You can go read those if you want. So adequacy is, the problem is we can't get what we want. Is what this comes down to. For example, when we have our test suite, we want to make sure that it is actually testing what it is we want it to test, and that actually covers everything adequately or sufficiently. Hopefully, you've seen in the past that this is not actually possible because of the halting problem, because it comes up with a lot of provably undecidable situations, like how do we know that this piece of code is even going to compile or if it's going to halt? Much less can this test case actually cover all the possible combinations. So unfortunately, we cannot write a program that can actually test whether our test cases are covering what it is. So instead, we have to come up with some type of weaker proxy. In other words, we have to determine different ways if our tests are sufficient for what we need. And that's what this section at least is going to talk about from a high level. What it comes down to is most of the time we think of rules. A great example that they're going to come up here, or here we go, here's a couple examples. The roof must have a pitch of at least, maybe it's 3/4 of roof pitch or something higher, just to make sure that, water actually rolls off of your roof. Now, this rule does not guarantee that your roof is actually good. I mean, we didn't say that it couldn't be holy, for example. But the idea is that if we have these rules, and at least give you some confidence that the code or that your design is meeting what needs to happen. And that's what we need to understand, is that these adequacy criteria are not going to ever prove that your test cases are completely good or accurate, but they are going to at least give you confidence that they're giving you what you're looking for. All right, so here's a lengthy example they go through. Specification describes different treatments in two cases, but the test suite does not check that the two cases are in fact treated differently. Then you may actually have something, you may not, then your results are basically junk. And that's what this idea is coming up with. Practical inadequacy criteria. Namely, if the test suite fails to satisfy some criteria, aka that we want to place on the test suite, then it's not actually proving that it is what we want. This goes back to the idea of the roof pitch. If you're building a house, you want to make sure the roof is within certain pitches so that the rain falls off correctly. Similarly, we want to come up with different criteria for our software to prove, or at least give us confidence that our test cases are testing it correctly. And then if our test cases pass, then we have some confidence that the software is actually running effectively. Going back with the building codes, keep in mind, we're going to keep, the book harps on this a lot, but this is very, very important. You wouldn't buy a house just because it's up to code. If you have all these codes up here that the house is good, you may not buy it. Maybe you don't like the way it looks. Maybe the architecture is badly designed for what you need, or maybe it doesn't have what you're looking for. You have a lot of kids, you need a lot of rooms or bedrooms or something, or maybe you're just a couple and you're not going to have any kids. Maybe you don't want a large house. And so just because the house is up to code and meets all the government codes may not be what you need. So that's why we need to come up not only with the criteria, but maybe some extra criteria. But it's also keep in the back of your mind that your criterion are not going to cover everything that's possible. But hopefully if you select these correctly, it'll cover the vast majority. So some useful terminology. This is where we're going to start going at least a little more practical. So your test case is basically a set of inputs, some execution conditions, and basically pass-fail criterion. AKA, you put these inputs into your program, you expect this output. That's a test case. So specification is a requirement to be specified. The obligation is the particular test case specification. And the suite, of course, is this group of test cases. And the actual test or the test execution is executing all these test cases and hopefully getting back some result. Hopefully that's useful. Let's see, the adequacy criteria predicate that is true or false of a program. And this is, hey, your program, is it actually registering credit card charges correctly? Or another criteria maybe, can users actually log in or be denied login with improper credentials? Those are different criteria. Of course, you're going to hopefully have a test case to test the different situations. What happens when they, for login, what happens when they put in the correct credentials, what happens if they don't, and then probably a couple corner cases of putting in some strange inputs, maybe try and do some SQL injection or whatnot as well. So where do these obligations or the criterions, as I like to think of it, come from? Well, the two big ones to first look at that you'll be dealing with most of the time is functional and structural. Functional is the black box, aka you don't know the structure of the code, so you're just looking at from the specifications. All right, they have a username, login, your username and password login, so you're going to put in different usernames and passwords, see what failed, and see how the code behaves. Structural means you're coming from the code, so now you're going to actually look at the code that handles username login and try and do an analysis to see if there's any errors inside of the code. And those are the two that you'll probably see a lot of. There is model-based, which we will be talking about in this class, where you're going to come up with a certain model and you'll be testing the model to make sure your design of the code is correct. Another example is fault-based. Maybe there's a fault or a problem, just power goes down, maybe you lost your connection to the database which stored the username and passwords. So how are you going to handle those types of situations? So the adequacy criteria is the set of obligations. This is what I was thinking of as a criteria. So your obligations from the set is your criterion, which is your high-level look or idea of what you want to pass. If all the test cases succeed, that's a pass. Every obligation is satisfied by at least one of the test cases. So notice that you're going to have your obligations or your criteria, which lists what needs to happen, and hopefully you're going to have your test cases that test those criteria. And that's what this example is actually talking about, what your book is talking about. So satisfiability, it's important to note that sometimes you're not able to satisfy criterion. For example, there's very good programming practice for doing defensive programming, something that can't happen. So Z, you don't want it to be, negative. Well, actually, this is a bad error because 0 is not positive either. But Z must be a positive integer. That should be a 1. But the idea is that if you're trying to do statement code coverage and you want to see what happens if Z is negative after this, well, maybe you can't do anything. Or furthermore, with the defensive code, maybe the check to make sure that it was positive was also up here somewhere. So there's no point or any test case that you can use to actually get to this line of code as well. So the point is here that sometimes a test case may not be able to satisfy all your criteria. So A, exclude any unsatisfiable obligations. Well, that's usually a pretty good idea if you can modify statement coverage so it can do it. But make sure we can't know for sure which are executable. This program is going to explode different code paths. So the problem with approach A is sometimes it's just not feasible or not practical. Another way to do it is come up with percent coverage, and that's where you're going to see a lot of this. B is what's done a lot, is that, hey, you want 85% code coverage. So we're saying, it's good enough if we can get 85% of the code. Fortunately, coverage, while it's used a lot because it's an actual practical tool, can be somewhat harmful or misleading, in fact. And what I'm talking about here, just to make sure, is that let's say you have a bunch of test cases, and your criterion is code coverage. You want to make sure you cover all of the code in a program. And maybe the test cases do about 85%, which is actually pretty good. And they want to know, is this actually a good measure of coverage? Well, this can help tell you progress towards throughout the whole suite, and it's really good for your business person. They want to know, okay, it's 85% tested, is what they think, although that's not exactly true. But it can also help you pinpoint trouble spots. Unfortunately, it can be dangerous because maybe your code coverage tests everything, but maybe it doesn't test all your branches at a certain point. A lot of times testers will actually try and just improve your code coverage without actually trying to improve the quality of the code. So they'll be writing a bunch of test cases that are really just superfluous, and that's going to happen a lot. When it comes down to it, the business person really wants to know what the cost-effective measure is. Unfortunately, they don't always understand what that means, but they really are coming for what's cost-effective. It's not needed to write those extra superfluous test cases. We need to focus on these parts of the code that are actually being difficult. And maybe that's part of that extra 15%, or maybe it's not. Unfortunately, this percentage can be somewhat misleading. Fortunately, I'm going to have to stop there and basically say that's where we've left it off for at least this chapter. Just recognize that that issue does exist. One last thing that this chapter does cover, by the way, we're doing chapter 9 here, and we'll also be doing chapter 10 this week. Not because we're trying to play catch up, just 9 and 10 really go hand in hand. But the last thing to talk about is different comparing criteria. There's something they want to talk about where how do we distinguish between a strong or a weaker one? Well, you can do an empirical test, basically study the effectiveness of different approaches. How effective is code coverage? How effective is branch coverage? So forth and so on. It's what we care about, but unfortunately, it really depends on the program. I mean, if it's a complete medical device where people's lives are at stake, then maybe you want to have near 100% code coverage as well as other characteristics for criteria, and that would make sense. But for certain apps and whatnot, maybe it's going to be a lot harder to decide what it is. So it ends up being more of an analytical approach, which is harder to sell. But it's an analytical approach to describe conditions under which one criteria is provably stronger than another. Stronger basically gives you stronger guarantees that the program is actually working, or overall effectiveness. So unfortunately, there is no good answer for empirical versus analytical. But the one thing that you can look up and that you will be doing for your homework is something called the subsumes relation. And this intuitively should make sense. If you have two criteria, but one is completely a subset of the other, then it subsumes it, in which case you don't really need that extra criterion. It's handled in the other one, and in which case you can just focus on that one. And that'll help simplify not only your criteria, but possibly your test cases as well. So here's an example: exercising all program branches subsumes exercising all program statements. So if you're doing full branch coverage, then chances are you're doing all program statement coverage as well. Although I will tell you that both of those characteristics are still labeled out, because in general you're not going to get 100% branch or 100% code coverage. Commonality compares closely related criteria, useful for working but from easier to harder levels, but not a direct indication of quality. Again, none of these criterions that we've talked about, and I think this is the end of that we've talked about so far, are going to cover everything 100%. It looks like we've got one last slide. So this is really just talking about how we can't guarantee that our test cases are covering all our criterion. We can't guarantee that test cases are actually testing everything, is really what we're talking down to. So what are other ways we can go about doing that? Well, you have to select your different test cases. You can try and reveal maybe something that's missing. What have I missed in this test suite? You can go investigate it. Maybe you can do some type of code analysis as well. But most of the time you have to sit down, you have to look at it from your software test as well as from your design. There is unfortunately no silver bullet for this problem. And that's what Chapter 9 is basically telling you. There is no silver bullet for trying to figure out if your test cases are going to cover everything. You really have to sit down and determine how much confidence your test cases are giving you that a certain piece of software is operating correctly. All right, that's it for 9. Soon you'll be seeing 10.